Yo, what is going on, physics class? This is Mr. Lopez coming at you with another physics lesson. This time we're going to be talking about section 18b about detecting electrical charge. Right? In order to study electrical charge, we must first be able to detect it. So let's go ahead and talk about a device known as an electroscope that was used to detect electrical charge. All right, so this is a picture of a common electroscope. It is a glass flask with a rubber stopper towards the top of it, and going through the stopper is a metal rod. At the end of the metal rod is a knob, and at the bottom, I'm not sure if you can see it. I can't see it, so you probably can't see it, but there are two foil leaves at the bottom, two pieces of foil that kind of just hang there. And depending on the movement of the foil, that can detect electrical charge. So here is a drawing that illustrates the general charges of the electroscope at any point in time. So what happens when a charged object is brought near the knob of the electroscope? Well, looking at this diagram in this first picture right here, you guys can see that through the rubber stopper is a metal rod, and this thing is neutrally charged, right? It has both plus and minus charges, right? So it's just kind of neutrally charged, and because it's neutrally charged, the metal leaves at the bottom, the two different metal leaves right there, they just kind of hang there. All right, so these two metal leaves, let's go ahead and color them green. All right, they kind of just hang there. Okay, let's make it red. It'll probably be easier to see red. I bet. Red. All right, they're just kind of hanging there. Now, here we have a negatively charged rod. All right, and what happened to all the charges? If you look at our original picture, our charges were plus, minus, plus, minus, plus, minus, kind of evenly distributed between positive and negative charges. But as a negatively charged rod is brought near it, the positive charges go up towards the end. All right, why? Because if you guys remember that opposite charges attract. Okay? So the negative charges and the positive charges are attracted to each other, and if all the positive charges are at the top, that means that most of the negative charges are at the bottom. And if you notice, what happened to the leaves? First, they were just hanging there, but now they're kind of separated, going in opposite directions. Why? Because now most of the negative charges are at the bottom and they are repelling. So if opposite charges attract, then like charges repel. All right. The same thing, the converse happens, works as well, where if I have a positively charged rod, so we have a positively charged rod, then it's going to draw the negative charges to the top. Why? Well, if it's positively charged, that means it lost some electrons. That means it wants to attract the electrons towards the top. And if most of the electrons are at the top, then that means that it is positively charged on the bottom. And because these are like charges, they're going to repel and push the foil leaves out to the side. All right. What would happen if I take this rod away from it? Well, if you take the rod away, then it kind of reverts back to this stage where the charges will kind of neutrally lay and the leaves will hang at the bottom. So what would happen if we made contact with a charged rod? If we happen to touch the knob of the electroscope? Well, looking back at this diagram, you guys can see that we have a zero net charge. This thing is neutrally charged. And we're going to go ahead and bring a positively charged rod and we're going to make contact. So what's going to happen? Well, because the rod is positively charged and because it makes contact, the electrons travel off of the metal and they actually go up towards the rod and they go ahead and match with all the positive charges. So what happens to the electroscope? Well, because it pulled a lot of the electrons, it leaves this thing mostly positively charged. If the electrons traveled through the metal sphere up into the rod, then now it lost electrons. It's mostly positive, and because it's positive, it's going to stay positive. When we had the original drawing and we brought the rod near it and then we pulled it away, it went back to normal. But when you make contact, it leaves it charged. All right. If you make contact with another positive charge, what happens? Well, it draws more electrons through the electroscope, and now it's even more positively charged, and you can see that this thing is even repelling even further. All right, it has a greater net positive charge. All right, so interesting to see how the electroscope works. Now, there are two different ways to charge something. One, you can make contact, which is what we kind of saw with the electroscope. When we made contact with a charged rod, it left it charged. So a charged object touches an uncharged object, and the electrons are transferred from one to another, leaving it charged. Okay. You can also charge a body by what is known as induction. When the electrons on the surface of an uncharged object are redistributed by a charged object that is brought near. So we saw two different cases. We saw this case right here where the charged rod was brought near it. That is an example of induction. All right, but it did not stay charged. All right, it was a temporary charge. So this was a temporary charge. In this case right here, it stayed charged, and that's because it made contact. Now, once you establish a charge, how is a charge lost? Well, an electrical ground, so I'm going to go ahead and highlight this, an electrical ground is when a large body whose charge is unaffected when the electrons are added or removed. So think of the electrical ground concept as an actual ground. All right. Basically, when it comes to electrical ground, we want to make sure is that the body that is transferring, that the electrons are transferring into, overall, there's not going to be enough of a difference. If you add a few electrons into the actual ground, like I'm talking about the actual Earth, I'm trying to find the right color. What color? I guess green. Ground. Boom. If you have like a metal rod going into it and you have some electrons going into it and they travel down into the ground, overall a few electrons into something as large as the Earth wouldn't make a difference. Okay, so that's why we use ground. The way that I remember this, me specifically, is if I looked at like a Pokemon type chart, all right, and you notice that if an electric attack is used on a ground type, all right, electric attack is used on a ground type Pokemon, notice there is 0 effectiveness. Why? Because electricity does not affect the ground, all right? So something to kind of keep in mind, that remember that ground Pokemon are immune to electric attacks. All right, why? Because electrons going into the ground honestly doesn't make that big of a difference. All right, so while electroscopes might be good for measuring charge, what about electric force? All right, so what we're going to do is we're going to go ahead and use Coulomb's law in order to measure electric force. All right, so Coulomb's law is stated as the electrical force is equal to K times Q1 Q2 divided by R squared. It might be easier for you guys to use this. I'm just thinking about plugging this into a calculator. It might just be easier to put the K in the numerator. Obviously, you guys are mathematically savvy enough to know that. But K is a proportionality constant whose value depends on the units used, and we'll talk about that in the last, I believe it's the last slide. we should also note that Q represents a variable quantity of charge with no physical dimension. So it's also called a point charge. Q represents the amount of charge. And I mean, this is a theoretical physics class. It's kind of theoretical. We're going to be calling it a point charge, where it just represents a charge of an object. All right, so this is the same formula that we're going to use. All right, really not that big of a deal. We're going to be plugging some numbers into it. Now, also stated by Coulomb's law is that the electrostatic force on each charged object, so we're thinking about two different charged objects, we're trying to figure out the force between them. The electrostatic force is equal and opposite to the force exerted on the other object, meaning that if we have two objects, let's go ahead and draw like a little diagram to help us out. Let's say we have two objects. We'll call this Q1 charge 1, Q2 charge 2. All right, and let's say that they are attracted to each other. All right, so there's a certain distance between them. All right, because the forces are equal and opposite to each other, there's no way that one force is gonna be having like this much. Like let's say this was, I don't know, 5 newtons, and this was 1 newton. All right, there's no way that one is going to have a stronger charge than the other. In fact, they have to be equal and opposite. So instead of being 5 newtons and 1 newton, what's more likely is that they would have to go right down the middle and be 3 newtons of force each. All right. So equal and opposite. Equal in magnitude, opposite in direction. Let's go ahead and look back at some stuff we've talked about a long time ago, and notice that this new equation for the force of electrical force is very similar to this equation which we talked about for the force of gravity. Notice the similarities. They both have a constant that goes in front. They both have, well, one has Q1 and Q2, the other one has two different masses. They both are divided by radius squared. So interesting enough that we can draw direct comparisons between electrical force and gravitational force. Both do measure force, so that's cool. Both are central forces, and both are conservative forces. But here are a couple of key differences that we should kind of be aware of. Electrostatic forces may be attractive or repulsive, meaning that if I have a point here, Q1 and Q2, they could either be attracted to each other or they can actually be attracted away from each other. All right, where one goes in one direction, the other one goes in the opposite direction. That is possible. For gravitational forces, we said that they are only attractive. We remember that if we have a large body and a small body, all right, the smaller body is always going to be attracted to the larger body. All right, so gravitational forces are only attractive. That's one key difference. Now, let's go ahead and talk about units of charge. All right, so there are a couple of different units of charge. The first one we're going to talk about is the electrostatic unit, or it's called ESU. All right, and one thing that you guys should know is that we can measure them in a few different ways. If a problem ever gives you units in ESU, you can say that K is equal to 1 dyne centimeter squared ESU squared. All right, so by definition, it is defined as that. If they give you the more common units of coulombs, then you would have to use this K value, which is the K value in coulombs. All right, and that would mean, and this is the way more common, more than likely you guys will be using units in coulombs. All right, and this is the equation that you would do. You just go ahead and plug this number in for K, Q1, Q2, R squared. All right, cool. All right, that's it, guys. That's it. That's all I got. See ya.